Hello, I'm Pei Wang. I'm going to present this paper in Architecture for Real-Time Listening and Learning. It is done by me and two of my students. For real-time system, we usually mean a system where the problems have time requirements attached to them. Usually, it can take two different forms. One is so-called hard real-time. Usually the requirement takes the form of a deadline. And some other real-time systems have soft real-time, in the sense that there is no deadline, but the utility of the solution will decrease over time. That is, it becomes less and less valuable. But we can see actually the former is a special case of the latter, where it just at the deadline, the utility or the value of the solution swap from 100% to 0. And usually, no matter which type, they're usually designed for special situations by taking algorithm, hardware, software, all the factors into consideration so as to satisfy the time requirements. And this one works very well in general, but for AGI, it's not good enough because first, you see, we are talking about general purpose system. So very often you don't know the task in advance until it shows up, and actually a new task can appear at any moment. And also the time requirement attached to it can be very different, even for the same task. If it occurs in multiple times, then each time it may actually come with a different time requirement associated with it. And also, when you are processing the task, the time requirement can change explicitly or implicitly as the situation or the environment change. So in this situation, we cannot really guarantee satisfy all the time requirements or the deadlines. Instead, the best we can hope is for the system to work kind of like any time algorithm. That is, it can always produce the answer, but when you give it more time, the answer will have better quality. The only difference is here we don't even have an algorithm for many tasks to follow. So if this is the situation, that's what you can do. That's what this paper is about. So we propose architecture, which is architecture used in our NARS project, which is an AGI system that adapts to its environment and can work with insufficient knowledge and resources, including to work in real time. This system can work in real time. Part of the reason is designed as a reasoning system. So every task corresponds to an inference process which consists of multiple inference steps. And in each step, a task interacts with a belief of the system by following an inference rule, which is an algorithm with a constant time and space cost. And the task NARS can handle at the moment, including a new piece of knowledge to be absorbed, a goal to be achieved, or a question to be answered. Since there is not necessarily a task-specific algorithm, then what the system does to a task actually depends on the beliefs selected at the runtime. And because the belief is going to trigger certain inference rules in a data-driven manner. So the actual processing of a task is actually determined by the number and order of beliefs selected for it. And that selection is highly context sensitive rather than determined in advance. So when there are multiple tasks, they are processed by the system in a time-sharing manner, like in an operating system. But here the situation is different because they have different processing speed, meaning that some of them are processed more often than some others in this time sharing process. And which it depends on the relative priority. So the priority indicates the relative share the system can get in this time computation or time sharing process. Similarly, when there's a lot of beliefs on which one will actually be used for a relevant task, well, that's also prioritized, and some beliefs are used more often, some of them are used less often, based on a priority. So for both cases, a priority value actually is a summary of many factors which should be taken into consideration in the selection. So this overall process is what we call a controlled concurrency. To support this mode of work, we use a new data structure called a bag, which is basically a probabilistic priority queue combined with a hash table. There are three major operations. One is you can put a new item, which can be either a task or a belief, into corresponding bag. The only difference compared to a conventional, say, priority queue or a hash table is here, each bag has a constant capacity. So when the bag is full, the item in it with the lowest priority will be removed. And when you want to take something out by priority, is not the one with the highest priority, which is taken out just like in an ordinary priority queue. In a bag, in principle, every item has a chance to be selected, but they have different chance. So their chance is kind of like correlated to their priority value. So high priorities will have a bigger chance to be selected. And finally, we still support the ordinary hash table operation, like you can take out an item by key. So supported by this data structure as well as by the controlled concurrency of control strategy, in NARS, each task is processed with the available knowledge and resource, and the system overall is trying to do as much as possible as far as the current resource supply, including processing time, is concerned. So it's very flexible, so it will allow various types of time pressure we mentioned before, and we'll try to use the time as efficient as possible overall. So what we believe, and we also argued in the paper, is that to work in this type of real-time is not just an implementation consideration, but is also made an important theoretical difference. Part of the reason is many practical situations require the system to work in this way, and as soon as you want to work in this way, we'll see that many traditional architecture is not going to work at all. So there are some major change need to be made, and in this paper we suggest such architecture. Okay, thank you very much.